Sometimes the most profound discoveries come from the most unexpected places. Today, we're diving into exactly that, how a wildly abstract mathematical idea, a shape that many people thought was literally impossible, somehow became the key to understanding the very fabric of our universe. It's a wild story. Okay, so it all kicks off with this massive cosmic mystery. For decades, physicists have been wrestling with this question. Our best, most advanced theories all suggest there's more to reality than what we can see. But where is it? Where is all that extra stuff hiding? And at the very heart of that mystery is this number, 10. See, for our most ambitious theories, things like string theory, to even have a chance of working, the universe can't just have the dimensions we know. It must have 10. And right there, that's the big problem, isn't it? We experience a four-dimensional world. You've got your three dimensions of space, up, down, left, right, forward, back, and then you have time. So if the math is screaming 10, then where in the world are the other 6? How can they possibly be real if we can't see them or feel them? Well, to find the answer, we have to hit the rewind button. We're actually going to leave physics behind for a moment and jump back in time, all the way back to the 1950s, into the world of pure abstract mathematics. And this is where we meet our main character, Eugenio Calabi. Now, you got to understand, Calabi was not trying to solve the universe's biggest problems. His colleagues described him as transformatively original, which is a fancy way of saying he didn't just solve existing problems, he created entirely new fields of math to think about. Yeah, his longtime colleague Jerry Kasdan really put it perfectly. Calabi's genius wasn't just about finding the right answers, it was about asking these fascinating questions that nobody else was even thinking about. He always took the less obvious path. So Calabi was deep into exploring this concept called a manifold. It sounds really complex, but the idea is actually pretty simple. A manifold is basically any space that looks flat when you zoom way in. Think about the Earth, right? We know it's a giant sphere, but the little patch of ground you're standing on seems perfectly flat. That's the idea. So in 1953, Calabi proposes something that was, well, pretty radical. He imagined a special kind of manifold, one that had this perfect, built-in balance. A property so specific that its curvature would always average out to 0, no matter how it was bent or twisted. To his peers, this just sounded too good to be true. They were pretty sure a shape that perfectly behaved was just plain impossible. And this is what he was picturing in his mind, a beautiful, intricate, mind-bendingly complex shape. At the time, this was nothing more than a ghost, an idea living only in the abstract world of geometry, an elegant figment of one mathematician's incredible imagination. But here's the thing in mathematics. An idea, no matter how beautiful, is just an idea until it's proven. And proving Calabi's conjecture, well, that would turn into a dramatic multi-year race. And here's where our second key figure enters the story. Shing-Tung Yau was a young mathematician who became completely obsessed with the Calabi conjecture. But here's the twist. He wasn't trying to prove it was right. He was a skeptic. He was dead set on proving it was wrong. And Yau's journey was a real struggle. He first came across the problem in 1970. By 1973, he was so confident he'd found a flaw that he announced a disproof at a big conference, only to realize, after a quiet question from Calabi himself, that he'd made a mistake. Talk about being humbled. He went back to work for 3 more agonizing years, and finally, on Christmas Day in 1976, he cracked the code. And with that, the impossible was made real. Yau's proof showed that these complex, elegant shapes Calabi had dreamed up could, in fact, exist mathematically. And so, in honor of both men, they were named Calabi-Yau manifolds. So, a beautiful math problem was solved. End of story, right? Oh, not even close. Because now we're jumping back to the world of physics in the 1980s, where that old mystery was still just waiting for an answer. Remember this question? String theorists were still trying to figure out what kind of shape those 6 extra hidden dimensions could possibly be curled up into. It couldn't just be any shape. They needed a very specific kind of geometry for their theory to even work. And here it is, the aha moment. Physicists stumbled upon the work of Calabi and Yau and had this absolutely stunning realization. This purely abstract mathematical object, this supposedly impossible shape, had the exact properties they needed to be the container for the universe's hidden dimensions. I mean, just think about that for a second. This is the incredible collision of two completely different worlds. What started in the 1950s as a geometer's abstract puzzle, 30 years later, it becomes the potential blueprint for the very fabric of reality itself. And the reason we can't see them? Because if this theory is right, those 6 dimensions would be curled up in a Calabi-Yau manifold that is just incomprehensibly small, less than 10 to the power of negative 17 centimeters across. That is far, far smaller than anything we could ever hope to observe directly. So what does this all mean? Well, it's an incredibly powerful story about the unpredictable nature of discovery. And really, it all comes back to the man who started the whole thing. Calabi himself said it best. He wasn't trying to reshape physics or find hidden dimensions. He was just pursuing a beautiful question in geometry for its own sake. The fact that it had this massive application, that was just a complete and wonderful surprise. And by all accounts, he was a true, humble genius. He kept doing research well into his 90s, scribbling these profound ideas on napkins and envelopes. He was known for sharing his ideas freely, never worrying about getting credit. To him, the point wasn't fame or application. The whole point was that doing math was simply fun. He once said this, and I think it perfectly captures his spirit. To follow your hobbies as a profession is the extraordinary luck I've had in my life. He saw his world-changing work as a hobby that he was just lucky enough to get paid for. And that leaves us with this final, fascinating thought. Calabi's story is the ultimate proof that we can never predict where the next great breakthrough will come from. It makes you wonder, what other revolutionary ideas, what future secrets of the universe are hiding in plain sight right now, scribbled on a mathematician's napkin somewhere, just waiting for the rest of the world to catch up?